So thank you everybody for coming. We're going to talk about FlexE. It's a new implementation agreement from done at the OIF, and it's real. It's here, and there's a bunch of places where it's being shown on the floor, and we just wanted to talk about some of the applications for FlexE. So Xilinx here today is honored to have two guest speakers, Tad Hofmeiser and Luca Chestia from Google and Cisco, and my name is Faisal Dada. I'm a system architect at Xilinx, and we'll all be talking about FlexE. So just to go over the outline of the presentation, we're going to do a brief introduction of FlexE, the enablement of FlexE and optical transport, some of the demonstrations that are on the show floor today, and then we'll have Tad talk about the role of FlexE in the data center and applications for system vendors, which Luca will talk about. So, as I mentioned earlier, FlexE is an OIF implementation agreement, and it was in my long career in telecom, it was one of the fastest standards that we've ever gone through. 12 months from project start, we had an implementation agreement done. And some of the reasons for that was there was wide consensus within the industry to make FlexE happen. There was lots of alignment between service providers, system vendors, and component suppliers. So key elements of FlexE are FlexE. What does FlexE do? FlexE is a method that allows you to physically connect pieces of equipment with a larger Ethernet MAC rate than is defined by IEEE. So IEEE today defines a 100 gig MAC rate. They're working on a 400 gig MAC rate in the future, but FlexE allows that MAC rate to be flexible. And it allows you to physically connect equipments together. So a router to another router, or a router to a transport box, as well as connect equipment over transport networks. So for example, two routers connected over an OTN transport network. How FlexE accomplishes all of this is by three basic principles. Something called bonding, where we can take multiple 100 gig E-lanes and bond them together to create a larger than 100 gig signal. Subrating, which allows you to take 100 gig links but partially fill them, and this would be useful in transport networks where you're not completely utilizing a 100 gig link. And then channelization is more of an MLG type application, where you can take multiple small Ethernet rates and put them inside the FlexE container or group. So we'll go over the attributes of FlexE. Bonding of multiple links is accomplished as shown here in the diagram. Here, where we have a 500 gig signal here, or 500 gig MAC rate that gets processed in a MAC, a FlexE shim, and then that gets distributed over 100 gig physical links, and that's transported over a FlexE group. In subrating applications, what we see is we have, for example, a 300 gig Ethernet MAC rate that's transported over 4 Ethernet links. Each of those Ethernet links has 75 gig of data on them, and they're transported over a transport network, maybe using QAM8 modulation to get 150 gig over each wavelength. And then they can be reassembled on the other side to get you a 300 gig data rate. Channelization, on the other hand, provides the ability to take multiple channels through a FlexE shim, put those channels in multiple 100 gig links, deassemble them on the other side, and then you can recreate FlexE to take them over to different pieces of equipment. So what can we do with FlexE? So a primary application of FlexE is connecting routers and transport gear. And what we've done on the show floor here is taken an FPGA that generates a FlexE group and an Acacia DSP system, and we've shown a complete enablement of a data center interconnect type application where you have flexible modulation rates on one side from a transport container point of view, and FlexE, which matches the client rate to that transport container. So just quickly go over those demonstrations. We can show a 300 gig signal which is transported over three 100 gig Ethernet PMDs and over 250 gig QAM8 modulation signals to the other side, or we can take a 200 gig signal that can be recreated going over two 100 gig PMDs using FlexE and use QPSK modulation for maybe a longer reach application or where impairments on the fiber are higher. So essentially meet the link budget requirements with client applications. That here is a setup of the demo we have up and running. If you look at it, it's an Acacia system here, a Xilinx FlexE implementation on an FPGA, CFP4, so CFP2 for client optics, long haul network on the other side, and the Acacia AC400 MSA board is taking two wavelengths of QAM8 to do 300 gigabit per second, or QPSK to do 200 gigabit per second. Essentially, another implementation can be, you could use a QAM16 modulation, for example, to do 200 gig, but instead of two wavelengths, use a single wavelength as well. Another interop test that we're showing on our booth is interoperation with the same FlexE implementation and a Testset. So the Testset actually can talk to FlexE, so you can see it's the world's first interop of a FlexE equipment with another vendor. That's just a brief introduction on FlexE, what we've been able to accomplish with FlexE in the last, since the IA was ratified and the public release went out 2 weeks ago. We've been able to put together some demos to show that this is a new reality. Now I'll I'll ask Tad to talk about some of the applications of FlexE within the data center. Thanks, Tad.
Yeah, we're excited at how quickly not only the standard went through, or the implementation agreement went through, but also that we actually have a live demo in OFC. This is great. So I'm going to touch briefly on the applications where we anticipate using FlexE in Google's network. So in Google, we have two backbone networks. One we call the Internet Backbone, or B2, which is essentially how we talk to customers through ISPs. And that has more nodes, but it's global. And then we also have the machine-to-machine or data center-to-data center network backbone. That's also global. And both of these networks are riding over transport gear that a large portion of our network is on leased fiber. So we're managing the transport gear as well as the routing gear. Managing and owning it. So if we look at a snapshot this is a similar use case that was just described on this interface between the router and the transport box. Now on these long haul transports, particularly the subsea, the cost of the fiber and the time it takes to light up a new fiber or light up a new line system is quite long. So we want to maximize the utilization of those fibers, which means we want to take the latest and greatest coherent transport. And if you're looking at the next generation DSPs, they're looking at having flexible modulation rates to squeak as much capacity as possible out of these fiber links. But what that means is it's not going to be on standard 100 gig or 200 gig increments. It's going to be more flexible and finer resolution bit rates. And in order to maximize that, we want to push those flexible bit rates through the transport gear all the way over to the router gear. But the client interfaces today, they want to be open and standard in order to interoperate between different vendors and using commodity client transceivers. And without FlexE, you're kind of locked into having the router card, port capacities, having to follow what the transport capacity is and what those PHY rates are. If you look in the past at when 40 gig E came out, it was a challenging mismatch, because getting 40 gig E into 100 gig wavelengths, you ended up straining 20% of your line side capacity. So looking forward, as the router rates are going higher and higher, we wanted to decouple that dependence between the routers and the transport, and FlexE enables that. So the first case is, if we look at 400 gig E, the NPUs are going up to 400 gig E, but we want to be able to utilize current technology DSP transport gear, which is, we're looking at 100 or 200 gig wavelengths. So that 400 gig router card, rather than having to now get a new mux sponder that does sort of a proprietary inverse muxing of taking a 400 gig on the transport, we want to be able to leverage these 100 gig or 200 gig transport boxes. And we can do that by bonding that 400 gig E. The FlexE shim will stripe that 400 gig E over 400 gig E client-side interfaces. The laser on here? How do I turn the laser on? Into these line card, onto the coherent line cards. And these members of this FlexE group do not necessarily have to be on the same line cards. And in this case, we can use legacy line cards that aren't even aware of the FlexE, because this bonded FlexE group, we terminate on the far end of the network at the router on this side. And because in this case, we are not doing FlexE termination within the transponders, the router does need to have a D-skew to do a realignment, because although they're following the same path, there's slightly different propagation delays at the different wavelengths, but it's on the order of a microsecond. Now the other use case is if we have a coherent transponder on the line side, and let's say initially we're at 200 gig, and we're fully utilizing it with 200 gig E's from 2 different routers. But let's say we have a fiber break, and we now need to reroute that path through the optical cloud. Whoops. I'm a newbie at this connector. Okay. We have to reroute that path, and now if that path can't support that higher order modulation rate, we need to back off on the capacity of that link. So in this case, I'm going from 200 gig to 150 gig. Now without FlexE, we'd have to lose one of those 100 gig clients and basically only fill that 150 gig with one 100 gig client. But with FlexE, we can throttle back on the transport, on the router side, we can throttle back to 75 gig. It's still a 100 gig client interface, and it's just sending 75 gig across. And in this case, the transponder, it doesn't need to have a full FlexE shim, but it has what we call a FlexE aware transponder. So it can recognize which of the unused portions of that 100, which time slots in that 100 gig FlexE group are not populated, and drop those and groom these 275s into a single 150 gig. This FlexE aware shim will also let us terminate a section layer control channel, so we can do a neighbor discovery, so we can validate which router ports are connected to which transponder ports. I'm going to hand it over to Luca.
Thanks, Dan. So let me start first. So let me start first to say something different. So Steve and I fighted a lot to get the FlexE out faster than what we did. So thanks for saying that it was faster. But Steve, I remember a call where we were not on the same page on the timing. So I think that we cover already what the data center expect from FlexE, and probably that cover also why FlexE as it come out. So there was the new idea of how to put the DSP with variable rate and make efficient the use of this variable rate from a router standpoint. Okay, what probably Ted did not highlight here is okay, what do we gain from a system standpoint? Okay, first of all, let's forget for a second the rate. We gain the fact that even if you want to transport over let's say, a multiple of 100 gigabit, you don't need to use an inefficient lag. So let's say I call it efficient lag. What does it mean? It means simply that you are not using an hashing algorithm to distribute traffic over multiple links. So what does FlexE? Distribute traffic, but in a way that does not affect how much traffic you are actually transporting, while all the lag mechanisms that are available today are based on layer 3 and burn some bandwidth in order to transport over multiple links. Then, talk already about the custom rates. So FlexE enable 25 gigabit increment. I don't think that we will really need to go down to 25 gigabit increment, but during the discussion of this implementation agreement, we didn't want to limit and enable that possibility. We match transport bandwidth. Okay, is again efficiency. We increase interface reliability. So this is a complex concept, but let me put it this way. How do you think that the 400 gigabit would be implemented? 400 gigabit PMD would be based on multiple 100 gigabit lane. Now, let's think ahead. So we may have also 1 terabit, 1.6 terabit PMD. All of them will be based on multiple lane. Now, why doing a single rate that if one lane fails, you get impacted, so the full interface would get impacted? Why not using behind a protocol that is robust to single lane failure and will allow you to keep up the traffic until you get the replacement? So this is the concept of interface reliability, in the sense that you are robust to a certain level of failures in the interface. And then there is a channelize and off. So Ted did not put into the data center application, and I understand that. So it's not probably in data center interest, the channelize and off, but imagine this. So I have a router that needs to talk with a traditional OTN network. And I have two options. Either I push the OTN inside the router, or I use some layer 2 trick to pass to handshake between the router and the transport. So FlexE will enable, with the channelize and off to transport, the capability to have a audio flex OTN switching application without putting OTN inside the router. So we covered already the other application, like reuse of FlexE aware and unaware equipment. Ted showed that you can use 100 gigabit or 200 gigabit transponder that are FlexE unaware, but actually FlexE is capable of doing even more, even using and adapting rate with FlexE aware device that are not capable to terminate the full FlexE traffic. Okay, let me explain better. I have 1 terabit interface in the router that has to interface to FlexE devices that are only 500 gigabit capable as maximum. And let's imagine these are FlexE aware transponder with variable rate. Okay, the FlexE will be able to, with the drop capacity of the that we implemented of the unused time slot, will enable the possibility to use those two transponders with the future router supporting an higher rate, and without the need to change the transponder because the router has a higher bandwidth. So substantially, what I put at the end of this page is breaking the marriage that had happened till now between the router and the transport boxes. Okay, let's go to the operating modes. I think I'm simply summarizing what I already said. So on the router, what we would expect to have. So we would expect to have a large pipe independent from the PND. And this means, said another way, the capacity to have, once a new MPU is available, immediately use it to the maximum capacity without waiting the definition of a new PND. And then, said in another way, the channelization is the flexible MLG. So I think that many of us know the trouble of defining the MLG and any, let's say, possible combination that the OEF was struggling with in defining MLG 1.0 and 2.0. So basically, FlexE implement the flexible MLG, and you will not need anymore to define, let's say, update the MLG depending on the PMD available. Looking on the transport side, there are, so what we need to say is, so what the transport will look like with the FlexE. So we talked already about the unaware mode, so reuse of 100 gigabit or 200 gigabit transport equipment, simply transporting 100 gig. And we talk about the aware mode, where we have, let's say, two ways of operating. So the full termination, where the transport is capable to understand the full FlexE rate and fully terminated, or the partial rate. That is exactly what I was describing below, and shown in the picture on the bottom, that I'm capable to use the third generation router with second generation FlexE transport box. Let's put it in this way. I think that this is all what I wanted to say.